Okay, all right. Okay, it's 11 o'clock. Hi, everybody. Welcome to DSCI 512. I'm very happy to see you again in another course in MDS. So in this course, if you are coming from a computer science background, you have had a course like this in your undergrad, which is a very detailed kind of course for a full term. But if you haven't come from a computer science background, that's quite fine. In this course, we will start from the very basics all the way up to the more advanced stuff that we're supposed to discuss. So don't worry about anything. If you have seen that meme or whatever that says, please tell me the name of a book that makes you cry and somebody sells its algorithm and data structures, it's not true for this course, so don't worry about that. Okay, I should have put it in the lecture, actually. All right. So in this course, this is kind of a continuation of the programming course that we had in the last block. So we have talked kind of briefly about the data structures and the kind of operations that you do on them. And then we introduced the concept of a class that kind of bundles all of these ways of organizing data and also the kind of operations that you would do on the data inside of a class. We've learned how to do it, but in this course we dig deeper into those concepts to see how the performance of our code will be affected by the kind of code that we write. So far in 511, for example, if you asked me if I have a nested loop or my code looks kind of messy, I would have told you that this doesn't matter, just write the code that gets the job done. But in this course, we actually consider scenarios where instead of, let's say, 10 data points or 100 elements inside of an array, you're working with billions of elements inside of an array, and you want to make your code as efficient as possible. And in this course, we discuss how you can analyze your code so that you can see if this code runs in a particular way that's going to be slow, in advance, or the ways that you can optimize this, or basically the kind of algorithms that you can choose based on the task that you have. And why the course is called Algorithms and Data Structures? This is because these two concepts, algorithms and data structures, have a very intimate connection to each other. We've learned in 511 that, for example, the kind of operations that are defined for an array or for a Python list are kind of different compared to the kind of operations that you do for, let's say, a dictionary or for a more sophisticated data structure like a graph, for example. You can imagine that we don't do things in the same way that we do for arrays, or we do for matrices, or we do for graphs and stuff like that. So this is why this course is called Algorithms and Data Structures, because with certain data structures comes certain algorithms that we can use to do operations on those data structures. Okay, so in this course, we won't spend too much time going in too much depth. The purpose of this course is to give you kind of a practical overview of what the topics are about. It's not about being able to implement all of the algorithms that we learn in this course. So that's not the goal here. The goal here is to give you enough confidence that when you see a code, you can build up some intuition about what the performance of this code is going to be like, and kind of making some predictions about the performance of the code. Okay. So about the course format, in the lectures we'll have kind of the traditional lectures that we had in 511, but I have, similar to 511, I have activities for you in the lab, which is kind of similar to worksheets, but you won't turn them in. It's just me talking about a couple of questions that makes you more comfortable working on the lab problems for the first half hour, 40 minutes of each lab. But the thing is, because one of the labs happens before the second lecture of each week, I won't be working on the questions that belong to the second lecture. So I'll post the activities. You can go over those questions yourself or ask me questions if you had any. But in the lab, I will only cover mostly the activities related to the first lecture of the week. Okay. All right. One last thing. So in the breaks that we have in the lectures, please let's focus them on the lecture content, not on lab questions, because lab questions are typically a bit more involved. And with my brain being a little bit slow in the mornings, by the time that I understand your question, the break is over. So let's do lab questions in the lab and lecture questions during the break. All right. So let's get started. Let me walk you through a couple of demos to see what's going on here. All right. So demo 1, searching. So here I'm creating a list containing 10 million elements, and these underscores that you see, they don't affect the program in any way. It's just a method to basically delimit or separate zeros inside a number. So these you can have them anywhere that you like. It doesn't affect the code. It's just for readability. Okay, 10 million, and I'm creating this range, and I'll show you the first 20 elements, and it goes on for 10 million values. All right. So now I want to check whether a particular value exists inside of that list. And in Python, we have this in operator, which works for any kind of container object. If you say this value in this container, it will give you either true or false based on whether it exists or not. So let's run that. It's false, obviously, because it starts from 0 all the way to the end of the list, which doesn't contain -1. And this particular function that we use is very useful for us in this course, because this %timeit, we have used it in 5.11, but here it's particularly useful. So this is not a Python thing, it's an IPython thing. So the thing that you're running in your Jupyter notebooks is not Python itself per se. It's a more enhanced interpreter for Python, which is called IPython, and it has these, for example, these magic functions that do stuff for us in a more convenient way, basically. This timeit, %timeit, basically just times your code. Instead of writing a bunch of code just for knowing how much it takes for a code to run, you just %timeit and run the code. Okay. All right. Taking a lot. Okay. So it says 110 milliseconds, and it gives you some standard deviations and average values, and it averages those runs over several runs so that you get a more reliable value for the average time. Okay, so this takes 110 milliseconds. Now let's create a different data structure. So here we created a list, as you can see over here. But here, let me do exactly the same thing, but let's do that with a set. So instead of a list, I do a set. And what's the difference between a set and a list? Exactly. Sets do not contain duplicates, because just like mathematical sets, they're sets, and they're unordered, so you can't index into a set. The values are just there like a bag of things. You can iterate over them, but they're not, you can't index into them. Okay, so let's create the same thing inside of a set. All right. -1 in x, okay. All right, now let's time this. -1 in x, now x is a set, and let's go. Okay, so 30.8 nanoseconds. And this is 110 milliseconds. So milli, micro, nano. It's the order around like a million times faster. Okay, that's a huge performance improvement. Okay, so in this course, this is what we're going to be talking about. If there was a way that we could have predicted this outcome based on the data structure that we use, and also questions like, what happens if I double the size of n? What happens to the runtime? So how will the running time be affected? Will it also double? Will it quadruple? Or does it increase by another amount? And also the reason behind why exactly this happened in this case. Okay. Any questions? Okay. So just a little tiny note here. The time that it takes to create a set will take longer than creating an array, and we'll learn in the next lecture why that's the case. So I was cheating a little bit here, but for the sake of argument here, the set is still much faster than an array for searching items inside of it. So you can ignore that. Okay, now let me walk you through another demo. Okay, so just before showing you the demo, I want to show you what these functions mean inside of Python. So we have a list like this one over here, and min and parentheses x is a built-in Python function that finds the minimum value for you. And we have some kind of similar function inside of NumPy that I think we have seen in 5.11, npmin. And okay, so I have to change this to a, so let me do this, np array, and here, let's do that. Oh, okay, I haven't done this. Okay, that runs, all right. And it basically does the same thing. However, there's another function inside of NumPy that can be pretty useful. That's called argument, meaning that instead of returning to you the minimum value, it returns to you the index of the minimum value. Okay. So here it says argument equals 3, and if we look at x at index 3, we can see the value 0.1, and that's the case because if we look at this this array here, you can see 0, 1, 2, 3, and that's the minimum value. Okay, so npmin, npargument, just two helper functions. All right. Now going back to the demo. So I'm creating a list with 20,000 elements inside of it, from 0 all the way up to the end of the list. Okay. Now I'm going to shuffle this X list around so that it's unordered. Okay. Shuffle. And then if you look at X now, you can see that it's unordered. It's just randomly shuffled. Okay, so I just created the list and then passed it to np-random-shuffle and then just shuffled it. Okay, I have a piece of code here. You don't need to worry about that. We'll talk about this tomorrow. It's just the code that basically sorts the list for you. Okay, you don't have to worry about this now. But let me just run this and wait until it completes. So 4 seconds already. Okay, it's taking a long time. Right, falling asleep. Okay, 12 seconds. Now just to prove to you that this actually sorts the list, you can see that the list is now sorted after the shuffling. Okay, now let's shuffle that again. Okay, and again just to see that this is actually shuffled, you can see it doesn't start from 0, 1, 2 anymore. Okay. Now let me do this. So x.sort. This is a NumPy sort instead of this is a Python sort instead of the kind of sorting function that I wrote. And let's see how that one performs. Okay, 0.2 seconds, and maybe it's good. Yeah, 0.2. And yeah, it's sorted. So there was a difference of 12 seconds and 0.2 seconds over here, and that was for 20,000 elements here, not for a million or a billion. Okay. Again, this is what we're going to be discussing in this course. Why did that particular thing happen? So why in the first case it took so long, why in the second case it didn't take that long? It's because the way that the sorting is done, the algorithm that's used for sorting is different between the one that Python is doing and the one that I wrote. Okay, and we'll learn how to analyze these cases and understand why that's the case. Okay. Any questions? Okay. All right. So I have another demo here for you. And this is something that we discussed a lot, I guess, in 5.11. So when you write your own loop to do something, and when you use the vectorized operations in NumPy, for example. So what was the difference between the two? Why the vectorized operations were much faster? Right, because the underlying code, instead of running inside of Python, which is very slow, it's run using libraries that are written in C and are actually in machine code. So there's no time consumed for translating the Python code into machine code and doing something. You do it in a much more efficient way using those compiled C libraries. So this is just a demo of that. So here I have 10 million items, and then I create X for random values, 10 million values here, and also 10 million zeros in Y. Okay, so X.shape, all right, 10 million, Y.shape, okay, 10 million. So again, random values here, zeros here. Okay, just to show you what the array looks like. Okay, these look random to me. And these are all zeros. Okay, so now suppose that I just want to multiply each value inside of X by 2 and then store the results inside of Y. And I can naively do this for I in range n and then multiply each element at index I by 2 and store the results back in Y. Let's run that. Okay, 2.3 seconds, not too bad. Now let's do the same kind of thing. Instead of using this kind of loop, I'm going to use vectorized operations. So again, redefine these. And now we know that this is vectorized. So the multiplication operator is defined with NumPy. And as soon as you do something like that, under the hood, NumPy goes and takes each element, multiplies it by 2, and puts it back inside of Y. And boom, 0.3 seconds. And it will actually be much faster than this if you have even larger arrays. I mean, comparatively. Okay, again, coming back to the same theme. How could we have predicted this outcome? And also questions like, what happens if I double or quadruple the size of n? What happens to the runtime? And the exact reason why this was the case. So again, we have already discussed the reason for this case. And this case is fundamentally different from the two previous cases. But this one is about using a different implementation of the code. So the kind of operation is still the same. You still have to go look at each element, multiply it by 2, store the results. That's the same between NumPy, between Python. Okay, it's a different implementation. But with the other first two demos, like searching and sorting, basically the algorithm, the way that we did that particular operation was entirely different. Okay, in the first one, the data structure was different. First one was list, second data structure was set, so we compared the two. In the second demo, the algorithm was different. So we sorted using my algorithm, and then we sorted using Python's built-in algorithm. Okay. All right, so before going a little bit deeper into the technical stuff, any questions up to this point? Okay, so time complexity. This is something that you will hear a lot when you're dealing with algorithms in general. So time complexity is concerned with the rate of growth of how much time it takes to run an algorithm when your input size grows. So time complexity is about the issue of scalability. So when you write a code, it works just fine for 1,000 elements. Can you guarantee that that code will still work fine for 1 million or 1 billion elements? This is a question that's of a very, very high importance in today's kind of data operations that we do. So typical databases today contain terabytes on terabytes of data. We have to be kind of sure that the algorithm that we use is the best one that is possible to use. So this is a very, very important question. And as a data scientist, you should know that the algorithm that you use, what happens if you grow the size of your data set? what should you expect? Should you expect to consume all of the computation resources in the universe? Or should you just buy, let's say, 10 more computers? That's a huge question. Because in the first case, it's just impossible. You just leave your job. But in the second case, there's actually a way to deal with that. You just buy 10 more computers and you're good to go. Okay. So again, just to recap, time complexity deals with the question, how does the runtime change as the function of the input size? It's not a function of anything else, just the input size. Okay, so let's see a couple of examples from the above demos. All right, so so find whether a number is in a list. So what happens to the runtime if we double the size of the list? How much more work do we have to do? And assume that the list is unordered. So you have an unordered set of numbers. You want to check whether a certain number is inside of that list. So if you have 10 elements, how many times should you check the elements? You have 10 elements. Basically, because you don't know what's going on, you have to suppose that those numbers are behind doors. You have to open each door and look for that particular value. If you know that, for example, you have a t-shirt, it's somewhere in your drawers, but you don't know where, you're sure that it's there, you have to check every drawer, right? So you have to do n operations. Now, if you double the size of that list, what happens to the running time? You basically have to do double the work, right? So 2n corresponds to double the work. It doubles. Any questions about this one? This is like, I guess for most of you, this is the first time that you encountered questions of this type. So it's perfectly fine if you have a lot of things that's puzzling you at this point. Okay. All right, so let's move on to the next one. Finding whether a number is in a set. If you double the size of the set, how much more work do you have to do? You might know the answer to this already if you have had this course before. So it's still the same thing. You have 10 numbers or 100 numbers inside of the set. What happens to the running time if you have 200 numbers in the list? Pardon? It shouldn't change. That may sound really weird to you. So the running time doesn't change. Whether you have 100 elements inside of the set, 1,000,000 elements inside of the set, if you're checking whether that element exists inside of the set, the running time does not change. Oh, that's interesting. And we'll learn why that's the case. Okay. All right, so sorting with, scrolling too much. Okay, so sorting with my code. If you double the size of the list, how much longer does that take to sort the set, the list? Sure, absolutely. Okay, let me scroll back up. All right, yeah. So you do this loop n times, basically. So what happens if you double the size of the list? So instead of n, you have 2n. How much more work do you have to do? And why is that? Why n squared? Okay, so you're coming from a computer science background. Okay, that's okay. We'll learn all about these stuff. So don't worry about that. This code is actually if you double the size of the list or the array, the amount of work that you have to do quadruples. Okay, so it goes up by 4 times if you double the size of the list. And the reason is that we'll learn in the next parts, we'll learn how to analyze this code to arrive at that result. Okay. I'm not giving you the reasons right now because we'll go through them one by one later. Okay. It quadruples, all right. So sorting with sort. And now this is the Python's built-in function. And if you remember, this one was much faster than my sort, right? So, just by remembering that, you know that it shouldn't quadruple, right? So it should be something less more work than that. All right, let's see the answer. So it slightly more than doubles. So kind of changes, kind of scales linearly with that. So if you double the size of the list, the amount of work that you have to do kind of doubles, almost doubles. Okay. And doubling, oh, okay, this one's interesting. So doubling an array with a loop. Now, in your array, instead of n, you have 2 n values. Okay, how much more work do you have to do? So you have, in the beginning, you had n values. Now you have 2 n values. How much more work do you have to do? So when you double the values inside of an array or list, you have to go look at each element multiplied by 2, go to the next, look at that element multiplied by 2, right? Okay. So it should logically double, right? That's kind of intuitive. Okay. Now, doubling an array with NumPy. Sorry, 1 moment. So with the list, you have, instead of n, you have 2n. Okay? The amount of work just doubles. We do the same thing with NumPy. Instead of n, you have 2n. Exactly. It doubles. All right. But it's much faster. So this is a very important point. The kind of analysis that we do here does not concern itself with absolute values of the running time. So we know that the NumPy thing runs much, much, much faster. We know that. But the scaling, the kind of growth in time, it still scales linearly. Okay, so if you have double the amount of elements inside of that array, you still have to do twice as much work, right? It doesn't change. There's no other way to do this. Okay, so this is a fundamentally different thing compared to the scenarios that came before this one. The amount of work still doubles, but it's much faster because it's a different implementation. This scenario is similar to running some code on my computer. Let's say that's a workstation. It's super fast. I run my code in 5 minutes. You do it on your own machine, you do it in an hour, okay? If I double the size of the data set, okay, it takes how much time on your computer? 2 hours. In the first scenario, it took 1 hour, now it takes 2 hours. In my case, it took 5 minutes. Now it takes 10 minutes. So it still doubles, okay? It's just the absolute amount of time that it takes that is faster, and that's a different thing. We are not concerned with those differences in this course. So we are concerned with the rate of growth of the running time as a function of the input size. Okay. All right. So before moving on to the next section, are there any questions? Yes. Mm-hmm. So you have an array, NumPy array that contains n items, 100 items. Okay, it takes, let's time t. Okay, if you double that, okay, then it will be 200 elements. So now time t will be 2t basically, right? The amount of work that you have to do. Oh, parallel. Okay, that's a good question. So the question is that if we do that kind of 200 operations, 100 operations, will that happen in a parallel way? The answer is no in this case. It could, but it's no in this case. So unless we implement, we will talk about that in later lectures, unless we design an algorithm that works in a parallel way, so part of that multiplication or addition operation is delegated to one core of the CPU, the other one is for this core, the other one is for this core, and these operations are kind of, let's say, decoupled from each other. Yes, we can do it in parallel and then combine the results back together. Yeah, but it's not in this case. Any other questions? Yes. Yes, that's the fastest, yeah. So Python has a way of switching between its sorting algorithm for different kinds of data sets. So it kind of actually optimizes that. So if you have an array or a list or something that's already almost sorted, there are like more optimized ways to do that. If it's entirely unordered, there are more optimized ways. So Python actually handles those cases, yeah. And if Python is slow, that's not because of its algorithm, it's because of its implementation. Yeah. Okay. All right, so ready to move on to big O notation. Let's see what's all this about. So we've discussed time complexity. And to recap, in this discussion of time complexity, we concern ourselves with how the running time of our code grows as the function of the input size. And in order to formalize that discussion and have a way to communicate this information to other people, there is a notation, like many other things in mathematics, there is a notation for that called big O. And it's shown like this, big O of something. And basically, big O tells us the approximate number of steps, the approximate amount of work that you have to, in algorithm, have to do as a function of the input size as n grows. So that last part is actually very important. Okay, let me add that in. As it's n grows. Okay. So you might have seen these other notations elsewhere. So little o, little omega, big omega, theta, and things like that. In this course, we only talk about big O. We won't go into the mathematical details of how big O is defined, but this is, the big O notation is not something just for algorithm, just for computer science. It's widely used in most other fields in mathematics that work with asymptotic analysis. Asymptotic, you may see in this word. Asymptotic means when the x or n or whatever variable we're working with approaches very extreme values. So when n goes to infinity, when n goes to 0, there are the behavior of functions basically change when that happens. So it's not, if you look at the middle values, it's something complicated, but if you take the limit to the infinity, you take the limit to 0, you've probably learned these stuff in calculus, things change quite dramatically usually. And in a lot of fields of science, we do those kinds of analysis in order to simplify things. So take n to the limit, see what happens. Take n to 0, see what happens. And in this case, with big O, we are concerned with cases where n goes to the infinity. We want to know what happens, at what rate does our algorithm grows in time complexity as n becomes larger and larger, and basically for very large values. So let's see what all that means. Okay, so I have a piece of code here, and it's a nested loop, and for n equals 3, you'll see 9 lines being printed to the output. Okay, so in this case, the time complexity of this code, if you double the amount of the data set, so in this case, n is just a proxy for the data set size. If you double that, it's 6, then the amount of values printed to the output actually become quadrupled. So in this case, we say that this algorithm is O n squared. What it means is that if you double the size of your input, the amount of work that you have to do quadruples, because n squared, so if you plug in 2n, that'll be 8n, so and it works out like that. So here I have a table for you for common values of the big O. So I have shown you a couple of different algorithms with different running times. So the cases where when we double the size of the data set, the amount of work that we have to do also doubles, that's kind of linear growth. So in that case, we say that operation, that algorithm is O n. The complexity is linear, okay? So if we double n, the runtime doubles. Okay, that's a very good thing. We also saw another case with sets. So we saw that the runtime didn't actually change at all, right? So whether you have 1,000,000 items in a set, whether you have 2 items in a set, if you want to see whether an element exists inside of a set, that just stays constant. It's not a function of the input size. In that case, we say that's O of 1, and we say it's constant. Why 1? And in the other case, why we don't say it's O(n), for example, O5n, or O5n plus 2. So we'll learn in the later parts of this, this section that in big O, again, we're not concerned about absolute values. Okay? So the rate of growth of 2n, or the rate of growth of 15n, is similar to the rate of growth of 0.5n. They both are linear. We're not concerned about the absolute values. This is why we don't write those coefficients, those factors, those multiplicative factors. And again, the behavior of, let's say, 6n plus 100 is similar to n. The behavior is the same. Both of these are linear functions. The behavior of all parabolic functions are the same. They just, the absolute values can be different. So in big O, we don't concern ourselves with exactly like how many steps it takes to do something. We are interested in how it grows as a function of time, as a function of the input size. Okay. All right, so here, okay, so here when we say that a function is cubic, the way that we interpret that is that we plug into n the size of the change data set. We want to know how much more time it takes for 2n compared to n. And in that case, we plug in 2n in that function, in that cubic function over here that you can see. And then we divide f of 2n by f of n. And then we simplify things, and in this case, we get 8 without worrying about anything else. This is a simple case. In other cases, we have to take the limit. So in the limit, the behaviors will be different, will be simpler, basically, to analyze. And we'll see how that's done in a later section. All right, so in this later section, I'll walk you through each of these algorithms, each of these different demos that we have done, and I will tell you what is the big O notation for each one of those. But before moving on, let's clear up any confusions if there are any. I know a lot of this might seem a little bit puzzling at this point, but that's totally normal. The key takeaway is that we are concerned with the time complexity as the data set size increases. That's all we care about. The rest of it is just notation, conventions for how you write things. Okay. All right. So, finding whether a number is in a list. So that operation, just as we discussed before, we had to go and look at every element in order to see whether a number exists inside of a list or not. Okay, so that operation, if we double the size of the list, the amount of work, it doubles. So we say that that's O(n). So it's linear. Okay, and again, we don't care if we do a lot of other things inside of that, that checking. We do some kind of other operations that takes like X amount of seconds. That doesn't matter. It's still all of that because the behavior is the same. Okay. So finding whether a number is in a set, and as we learned, that's O of 1, meaning that that's constant in time. It doesn't change as a result of the input size. So sorting with my code, that's O(n) squared, and let me tell you why. Okay, so we do this loop, and whatever we're doing here, we do it n times, right? It's a for loop. It does n iterations. So we're doing that thing n times. However, there's a catch here. This numpy function over here, this argmin, that's also a function that does n operations each time you call it. So within each of those iterations, you do n operations. So you have n iterations, overall operations. Inside of each one of those, you also do n operations. So that will be n squared. Okay? And that's why this case was super slow. So this thing over here does n operations itself, and this is a loop. So this is very similar to the nested loop that I showed you. So this is very, very similar to this one over here, right? A loop that goes, that iterates n times inside of another loop that also iterates n times, n squared. Okay. So sorting with .sort actually implements an algorithm that we'll learn about that has a complexity of n log n. So that's very fast actually, just a little bit slower than linear time, because log is a very harsh thing to do to a number, and it goes very slowly. Okay, so that's actually a good algorithm, and that's actually the best algorithm that's out there for sorting. Okay, and again, we'll learn about this in tomorrow's lecture, in the next lecture on Thursday. Okay, doubling with a loop. So what's the complexity of that? Just look at every number multiplied by 2. If you double that, the work doubles, so that's linear. Okay. And doubling with NumPy, and we've discussed this already. It's again all of n, so you can see the complexity is the same, although the absolute time that it takes is like much, much faster, on the orders of hundreds faster with NumPy compared to Python lists, but it's still the amount of work doubles. Yes. Okay, great question. So are the logs base 10 or base E or base 2 or something else? It doesn't matter. The behavior is still the same because logs of different bases are just different by a constant. So it doesn't matter. The log, again, this is another manifestation of the fact that we're not concerned about absolute values. We're concerned about the behavior. Okay. Well, so before moving on to the next part, let's have a break. 5 minutes, and then we'll be back with the rest. right. So we're back. Let's move on. So let's talk about how we can arrive at the big O notation for certain cases. So the way that we do this is that we look at the different kinds of operations that we do inside of our code. For example, we have a code, there's an ON operation here, and then we have a loop. Inside of that loop iterates n times, and then let me actually write that down here. So suppose that here, suppose that I have something like this. So I have an ON operation here, and then I have a for I in range n operation here, and here I do something O of n, and then I do something O of log n, and then I move on here and I do something ON again, or O5n. Okay, so in this case I look at those operations and I compare those different time complexities. The thing is, with the time complexity analysis, I can always disregard some of the terms for the other terms that are more important as n grows to infinity or to very large values. For example, I can always ignore constant time for O of n, right? Constant time doesn't matter. If n becomes 1 million, then 5 doesn't matter anymore, okay? And also the same thing goes with log. So with log to the base of 10 of 1 million, it's just 6, right? That's a small number, but n grows to 1 million, and that's, again, nothing to be concerned about. So we can always ignore log n compared to O of n. And same goes for ON log n for ON and n cubed, for example, compared to ON. So this is the order that the time complexity grows, and we can basically throw away anything that's smaller than the largest dominant term that we have. So for example here, I have ON here, all right, and I have, within this loop, I have ON, so this basically translates into something like this. The total amount of operations that I have to do here within the loop is ON squared, because I have an ON operation within a loop that iterates n times, that's ON squared. This one becomes what this will be outside of the loop? This n log n, right? Okay, because this loop runs n times and we have log n operations and log n. Okay, so overall I have to look at this one, and this one. Okay, so in the comparison, which one of these terms wins? Say it out loud. The squared, right. ON squared is much bigger than n log n, 5n, or n. If I didn't have this one, so what in this case? What's the dominant term? N log n, exactly. And if I didn't have this one altogether, what is the complexity of my code in this case? O of n, because the constant factor doesn't matter, it's just the same thing. So with the big O notation, if the algorithm takes 2n, we just write O of n, not 2n, that's what we just discussed, and we ignore lower order terms. So in n plus 5, for example, we don't write ON plus 5, we just write ON. And again, n plus log n, when n goes to infinity, the log n just becomes irrelevant, and then you just write ON. Okay. And this is, again, the most important thing here. We are concerned with this when n is large. Okay? All right. So something that I've seen coming up in interviews is that, so they try to puzzle you by the fact that, okay, we have an algorithm that is O log n, we have an algorithm that is ON, which one is faster? Okay, and they implicitly tell you something about the input size. So again, the important thing here is that ON is the time complexity is larger or higher compared to O log n only when n goes to infinity or very large values. For small values, O log n can actually be slower than O. Okay, so again, this all is valid for large values of n. In this case, for example, this 10,000 log n, is more than that 0.001 n for small values of n. Although this one is O of n, this one is O log n. The log n should be faster, but for small values, we can't say for sure. Okay, that's a very important thing to remember. And we will see examples of this in Lab 2, and I'll also have a visualization in the next section that actually demonstrates this. So let's say some of these time complexities on a plot. That's the best way to understand what's going on. All right, let's run this. Okay, so we have O(n) log n, n, and log n, and squared n all the way up to 2 to the power of n, 2 of n. So you can see that because 2 of n grows so fast, you don't actually see anything else. Okay, so 2 of n is exponential time, and it's like a terrible, terrible thing to do. You'll probably never do this, but we'll learn about a particular algorithm that actually is exponential in time, so it just blows up after a few steps. Okay, and in order to see things a little bit more clearly, I show that to you on a log-log plot. That's more clear. On a log-log plot, the spaces between the exponents are constant, not between the numbers. So it makes things compressed for large values and enlarges things for smaller values. So here you can see that. Constant time, okay, this blue line over here, all right, it just stays constant, is not a function of n. And you can see that, for example, log n, okay, that's log n. And the values such as O(n), O(n) squared, or O(n) cubed, those are all straight lines in log-log plots with a slope that's equal to the exponents. Okay, and you can see that these are all straight lines. Okay, and the exponential function is still exponential when you do it in log-log, but it's just more obvious the rate of growth of these functions. So you can exactly see this is constant. The log n is very slow, very actually fast in time complexity in your code runtime. The other ones are just constant lines with constant slopes, and then 2n, 2 to the power of n, which just explodes. Any questions about this plot or the other one, these visualizations? So O log n for smaller values of n could have a larger time complexity, or it takes more time than O log n. It could take more time. So O log n is supposed to be faster, supposed to take less time, but for smaller values we can't necessarily say that's true. And I'll show you an example of that. Yeah. Right. But this doesn't really demonstrate that, so I'll show you a plot of that. Okay, so I just remove the exponential one just for you to see the other ones on a log-log plot, just to be more clear about the different plots. So let's move into example big O analysis. And here I just want to demonstrate how we do this analysis, again, in a couple of examples so that you feel more comfortable. Okay, so let's, I gave away the answer, but anyways. So here we have a loop that's a function of n, runs n times. Another loop inside of that runs n times for each iteration of the outer loop. That's O(n) squared. Let's scroll carefully here. Okay, how about this one? What is the time complexity here? So look at the code. Look at the rough number of steps. O of n, exactly, because this loop over here, that's O of n. It runs n times in steps, or roughly in steps. This one also runs n steps, so the complexity is 2n. We just ignore the 2, and that'll be O of n. Okay. And now when you do this, you can confidently say, if you multiply the size of your data sets by 10, the runtime will also be multiplied by 10. You can make that argument. Okay, so this is just a description of what we have discussed. And, all right. So what affects the big O? The algorithm, just like we see how many steps you do. for a particular operation. What affects the constant? The algorithm, obviously, that's the first thing, but just like we discussed, the implementation also obviously affects the absolute amount of time that it takes for you to run your code. Okay? On your computer, it'll be something, on my computer, it'll be something different, so that's the constant that's at play. Okay? And right, like here I say your programming language, the library you use, how fast you use your laptop, whether you use parallel computation. So we'll talk about these in the later lectures briefly. Okay, so let's, for a little bit, let's talk about lower order terms. So we kind of already discussed this, but let's see this plot over here. Okay. You can see that n log n plus log n plus 5 compared to n. And just like we said, it kind of has a logarithmic curvature here to this function, to this orange one. But you can see that as n grows, they both become just straight lines. And this is what we have been discussing all along. Okay? And for lower order terms, for smaller n, that's the case that you were interested in. Let's see. Okay, we see something interesting over here. So square root of n is obviously, for large n, it's smaller than n. It just takes the square root, it compresses the number down. But you can see that for small values, that's not, square root is not always more efficient than n. Okay, and here, as we zoom in further, you can see that up to n equals 800, for example, square root of n is actually much slower. Right? So we can't always say that is true, but actually it's not correct to say that O of n in this case is larger for square root of n, because O of n is concerned with n grows to infinity, but you can still make the argument that the time complexity of square root of n is something larger than O of n in this case. Okay, you can see that the behavior is different for small values. It's only for the large values of n's then that this analysis applies. Okay. So when we say that we are only concerned with dominant terms, the term is something in a mathematical equation that is either added or subtracted to or from something. Okay, so n plus log n, this particular expression contains two terms, n and log n. And when you see something multiplied by each other, that it's in its entirety, that's a term. Okay, so n log n is a term by itself, log n is a term by itself, n is a term by itself. And when you discuss the dominancy, you look at the dominancy of each one of those terms and compare those to each other. Okay. All right. So big O with two variables. So consider this code over here. We have an outer loop that's a function of n, an inner loop that's a function of m. What is the time complexity here? N steps, m steps inside. Nm, yeah, I've heard. Okay, yeah, so that's the time complexity is nm, so we can't say that it's n squared, m squared, or just n, because unless we actually fix the values of any one of these two variables, we just have to say it's O and m, as simple as that. We can't go any further than that. So in this case, O and m. And if m was equal to n, like in previous cases, obviously that's m squared. And note that this is still a high order term. This is still kind of a square term because it's a multiplication of two variables. Okay, one thing over here to note is that we never write O and m as O n multiplied by O m. It's just a convention, okay? So never do this. And also we don't write O n plus m as separate, like O n plus O m. And in this case, we can disregard this m. That's a lower order term for nm, and we just write O n m. You have to always disregard anything that has a smaller dominancy. Okay, So in this case over here, you can disregard n compared to n squared, but you can't really say anything about m unless you have more information. So you have to say it's O n squared plus n. That's the time complexity. Okay. So in DSCI 571, I guess you have had a lecture already, right? DSCI 571. Okay, so with a data set that you have n rows, like n observations or data points, and you have d columns or d variables, so when you do the dot fit, that dot fit is at least order of n d, right? Because that's n observation, d column. It takes nd amount of time to at least look at each data point in that data set, right? So that's kind of like the lower bound on that. Okay, it's actually more than that because you have to do some other more sophisticated decision tree thing, and it becomes something like the nd is still there, but you also have a log n and you also have an m for the depth of the tree. Okay, so you can see you can still make some arguments about the complex. You say that it can't be smaller than nd. Okay, just we're good on time, I guess. Yeah, so let's discuss worst or best case average, worst, best, and average cases for a little bit. Yes. Sure. Right, exactly. So yeah, you have to keep all of them. Yeah, yeah. You don't know what's going on in there. Yeah. Yeah. Okay. Okay, so this code that we have over here finds 0. For xi in x, if the element is equal to 0, then return true. So x is just a list, and whenever we hit 0, we say that just return true. And in Python, when you return something, the execution of the function is terminated. You'll be back to the main program. Okay, so in this case, the time complexity of this is, what's the time complexity here? Say it out loud. O(n), exactly, that's O(n). But suppose that we know that the element that's equal to 0, it's right at the beginning. So as soon as you start the search, you say, boom, that's there. So in that case, the time complexity would no longer be O of n. That would be O of 1, exactly, because it doesn't matter if you have 1,000,000 items, if you have 1,000,000,000 items, that element you're looking for is still in the first position, so it takes constant time. That is called a best case scenario. And the same thing could happen that when suppose that these elements are randomly distributed, so it's kind of in the middle. If you average over a lot of different scenarios, you can argue that the element 0 could be found statistically somewhere in the middle. So the order of complexity is n over 2, and that's just O(n). Okay, so that's the average case. And the worst case is that element you're looking for is all the way at the end. So every time you have to start from 0, go all the way to the end, and that'll be exactly O(n). The time complexity will be O(n). Okay, so this is just a notion of when you have worst case, best case, and average case. And we don't really make this distinction in this course. It's just something for you that if this comes up, you know that based on the state of your data set, your running time might be different. But we typically you look at worst case scenarios, which is when you do the big O notation analysis, it's similar to the average case most of the time. It just varies maybe by a constant or something like that. So we're concerned with the worst case, which gives us like an upper bound on things. So we say that it can't take any longer than this. Okay, we're sure. So that's more reassuring for us as a programmer or data scientist. Okay, so any questions about this part before moving on to the next? Okay, so we're just going to discuss something similar to time complexity, and now that, yeah, question? that's exactly what we're going to discuss in the next section. So we have time complexity, the amount of time that it takes to execute some code, and also we have something similar here, space complexity. Okay, so it's basically kind of the same type of arguments that you can make for space. So you're not concerned with the amount of time that it takes, but how much memory you have to consume in order to store your data within your algorithm. And this is an interesting thing. So if in your algorithm you write something, it's very efficient in terms of the time, but you copy things 10 times. You put your data everywhere in the memory. That's not super efficient space-wise. Okay, so you can still have a large space complexity while you have a very good time complexity. Okay, so let's just run a few demos for you here. So we have this PS util package with Python that shows you the amount of memory that you have in your system. I have around 16 gigabytes of RAM. It says 50% of my memory is filled with data. Excuse me. And if a number, if you assume that a number takes up 8 bytes, I can store around 2 billion numbers in the memory. Okay, and we usually have other stuff going on in our system. You can see that right now I have 50% of my memory is filled. So it's much less than that. That's not entirely true because Python and the operating system actually does something clever. When your memory is full, it writes some of the data in the memory to the hard disk. So you can actually go beyond that 16 gigabytes or 8 gigabytes, but it's going to be much slower. Okay, let's just ignore that for now. So space complexity is concerned with the amount of space that you need to store your data. So here I create an mp.zeros. I'm creating zeros, n values. What is the space complexity? How does the memory size that you need grows as a function of the input size? Exactly, it's all of n, right? Right. So how about this one? MP0s, it's a matrix of n by n. It's n squared, right? Right. Yeah. Okay. And okay, how about this one? Zeros, n, n, and 5. So it's three-dimensional. N squared, again, that's n squared because the 5 is a constant, doesn't change. Okay. And again, note that the absolute amount of space that you need is still larger in this case compared to that one, but we're not concerned with that. Okay, how about this one, cubed? I'm just going to say that because n, okay. And let's run this. Yeah. Okay, so I just gave away the answer. NP0s, 5 elements. It doesn't depend on anything, so that's just a constant. Okay, interesting one here. So you have n users on your social network, okay, and you want to store the level of friendship between every pair. And suppose that the way that I think about my friendship with somebody else differs from the way that they think about their friendship with me. So it's directed. So what is the space complexity here to store all that data? So from each person goes one edge to all of the other people that we are considering. Pardon me? Right. Okay. So in this case, if you do the multiplication and ignore the lower order terms, you arrive at n squared, right? Because that's a simple case of permutation, basically. Okay. How about if you have n users on your social network site and you want to store who is friends with who? This is a case that it depends. It depends on, it's like it can have a worst case. What is the worst case here? Each person is friends with everybody else, right? That's the, I mean, it's not the worst case, I mean, from the analysis point of view. Okay, so in that case, that's again O n squared, but if we limit that number, so obviously we can get something O of n if we say that the maximum number of people we can be friends with, let's say, is 100 persons. Okay, so it will be O of n if we set a limitation, but the worst case, it's still O n squared. And we'll learn a bit more about this type of kind of graph things in week 3. Okay, so we're almost all the way to the end. Let me just show you this thing that I just brought up a few minutes ago. So here I have this 53% of my memory left, so I can store, with 16 gigabytes, I can store 2 billion. Now I can store around 1 billion. So here is my 1 billion. Okay, and if you do this, it's kind of an indication that the operating system is doing something fancy, because it hasn't filled up the memory all the way. It has left me something to work with, because otherwise the computer crashes. So if I look at this, you can see that the value checks out. We still have the amount of bytes that we're interested in, so around 8 gigabytes. And okay, get the size of, that gives us the values in bytes. And you'll use this function, get the size of, in your lab, just to inspect the size of variables for space complexity. Now, if I do something like this 3 billion, that obviously doesn't fit in the memory. And let's see what happens. I would have expected this to crash, but knowing that there's something that the operating system does, it actually doesn't crash. But you can see that it's slow. The operating system uses a technique called swap memory. Takes stuff from the memory, writes it to the hard disk in order to fit all that amount. And you can see that it's pretty slow, but it works. In the end, if you check the size, it's 24 gigabytes of data, but I have only 16 gigabytes of memory. And you can see that the memory consumption, that actually decreased because it has moved more stuff from the memory to the hard disk. So just something for you to be aware of when you're working with large data sets. You might be able to load your data, but it's going to be pretty slow because memory is super fast. Hard disk is much slower. All right, so any questions? Yes. Number of bytes, I'm not sure actually. I have to check the documentation. For some reason I have it in here, both methods, but yeah, I'm not sure. Maybe the n bytes, the get size of accepts some other arguments that will be helpful for you to read what kind of output you're getting, maybe. Yeah. Any other questions? Okay, so again, in the labs, the first half hour or so will be dedicated to activities. You don't have to turn them in. And so if today's lecture was something quite new for you, don't worry too much. We'll talk about all of these concepts in the lab with practice questions. And I have a bunch of interesting questions for you in the lab that you'll find them find them fun to do and find them interesting to work on. We have one question all the way at the end is above the Markov model. That one might be a little tricky. So do everything before that question 4, and if you had time, work on that question. And there's a bunch of challenging questions in there. All of the challenging questions combined, they account for only 5% of your total grade. You don't have to do all of them. Even you can just try a bit of them, you get some partial marks. We don't have auto-grading. We don't have auto-grading. You still receive partial marks if you do just a bit of that. So don't spend too much time on the challenging questions. Okay, all right, that's it for this lecture. Thank you so much, and see you tomorrow.